Welcome to All Things Data. Today we're going to dive into clustering. I'll first give an introduction on what it is, and then we'll cover 3 common approaches to clustering. This video will provide both theory and practical implementation. All code and resources are linked in the description below, so you can follow along if you'd like. Let's get started. Clustering refers to any non-parametric and unsupervised machine learning algorithm that forms clusters by grouping together data points that are similar to each other while ensuring that data points in separate clusters are distinct from one another. They are approximations and they do not guarantee optimal solutions due to computational infeasibility. However, they can still be useful despite this. Clustering can be used for many applications such as geospatial analysis and market segmentation. Before we get into our first clustering algorithm, we need to pre-process the data. Make sure to clean up missing values and duplicates. It may also be appropriate to scale and normalize the data if they are on different scales or if outliers exist. Additionally, dimensionality reduction may also be needed when dealing with large dimensions, correlated features, and simply for interpretability. The examples used will only have 2 dimensions and have clusters that are identifiable by eye. This is done in order to teach the concepts more easily, but in reality, the data will be higher dimensional and the clusters may not be discernible by observation. The first type of clustering is centroid-based clustering. This type of clustering relies on finding the center of each cluster and iteratively assigns points to that cluster, then updates that new center. The most widely used centroid-based clustering algorithm is k-means clustering. The first step is to choose k, the number of clusters that we want. The second step is to initialize the clusters. To do this, randomly choose k data points where each data point represents the centroid of its cluster. The third step is to assign all of the data points to a cluster. For a single data point, this is done by finding the Euclidean distance between that data point and all the cluster centroids. The smallest value will be the cluster that this data point is assigned to. The fourth step is to then update the centroid of the clusters. Remember that in step 3, more points were assigned to the clusters. This changes the centroid and therefore we need to update it by recalculating the mean of each cluster centroid. The last step is to keep repeating steps 3 and 4 until the clusters stop changing or a certain number of iterations is met. Here is a visual demonstration with the customer segmentation dataset. We are now going to visualize each step of the algorithm. Here is step 1 where we choose k, and k will equal 5. Then we have step 2 where we initialize the clusters. You can see the cluster initializations here. Then we have step 3 and 4 where the points are assigned to the cluster and updated. Notice how the cluster centroids move. You'll notice that the last 2 iterations are the same. This shows convergence and is one way to tell the algorithm to stop. For a small dataset like our example, it is unnecessary to add an iteration limit, but for larger and more complex datasets, it is necessary to do so. It's also important to note that the initial centroids affect the final cluster. We can compare this cluster by taking a look at clusters with different starting initializations. Notice how this is one big cluster, which was not apparent in the previous clusters. This is how we apply k-means clustering in Python. Make sure you import the necessary libraries. The k-means function has many function parameters, but only a few are needed. N-clusters specifies k, the number of clusters. Max iter is the maximum number of iterations for the function, assuming the clusters do not converge. And init specifies how the initial points are chosen. We now know how k-means clustering works, but there are two issues. We know that randomly choosing points each time can produce different clusters, so how can we choose the best cluster initialization? Secondly, we also don't know what k should be. Before we can answer these questions, we need to define two cost functions. The first is the within cluster sum of squares, or inertia, which measures the sum of squared distances for each cluster. A smaller inertia is ideal because it means clusters are more compact and therefore well defined. An interpretation of the equation is, for each cluster, get the sum of the Euclidean distance between each point in the cluster and the centroid of that cluster. Sum over for all clusters. The second is a silhouette score. It calculates how well a point is matched to the correct cluster, so a score close to 1 is ideal. The function SI is a score for a single point, where AI is the mean distance between I and all other points in its cluster. BI is similar to AI, except that we are comparing I to the mean distance to all other clusters and choosing the smallest value. To help choose the best random initialization, we can use the function parameter init equals k-means plus plus. This means that the initial clusters are chosen randomly, such that each cluster is spread apart. This causes faster convergence and lower inertia. Ninit represents the number of times the algorithm will run with different random initial centroids. When you combine these two, the algorithm will choose the initial clusters that result in the smallest inertia. Using the cost functions, we can also create plots to help choose the best k. For the elbow method, we want k on the x-axis and inertia on the y-axis. Notice that there is a sharp bend in the graph. This is called the elbow point, and its x value should contain the ideal value of k, which in this case is 5. For the silhouette score method, we want k on the x-axis and the silhouette score on the y-axis. Choose the k which produces the largest silhouette score. In this case, it is also 5. K-means clustering is the most commonly used centroid-based clustering method, but other algorithms do exist. K-medoids clustering is similar to k-means clustering, except that it uses median instead of mean. The biggest drawback is that it performs poorly on non-circular clusters. You can confirm this by going to the K-means clustering Shiny app and switching to the Donuts tab. Density-based clustering is preferred when it comes to non-circular clusters. It groups clusters based on regions of high densities. The algorithm for DBSCAN is fairly lengthy, but it is not too complicated, so instead I will explain it using an analogy. Imagine each point is a lost hiker at night. Every hiker wants to create a cluster so that they can feel safe. Every hiker has the same flashlight, and that flashlight can only illuminate a certain distance. The distance is the parameter EPS. Hikers cannot move, but they can shine their lights in any direction. If they make a full rotation and see a certain amount of hikers or more, then they will become friends and become part of the same cluster. Eventually, the number of hikers in a cluster can grow as they look for each other. The minimum number of hikers they must see is the parameter min samples, and it's also possible that some hikers are overlooked and not part of any cluster. Here is a visual demonstration with 2 moons. You may have noticed that the algorithm automatically selects the number of clusters. Therefore, we do not need to specify k. Another thing that you may have noticed is that some points are not part of any clusters and are labeled as outliers, shown in the red dots. This is unique to density clustering algorithms and can help deal with extreme data points. This is how we apply DBSCAN in Python. The parameters are EPS and min samples. We now know how DBSCAN clustering works, but there are 2 issues. How do we know the value of min value and EPS? Let's play around with extreme values of EPS and min samples. If min samples is too small, we will have too many clusters. On the other hand, if it is too big, then we will have too many outliers. If EPS is too small, we will have too many outliers. But if it's too big, we will have only one cluster. Min samples should be 2 multiplied by the number of dimensions, plus minus 1. For each min sample, we can use a k-distance graph to find its corresponding eps. To construct a k-distance graph, we first compute the kth nearest neighbor for each data point. In this case, k is equal to min samples minus 1. The second step is to sort these distances in ascending order. The third step is to plot this on a graph. The fourth step is to repeat for other values of min samples. We can plot out the k-distance graph for each min sample. Look for the elbow point and find its y value. That is the eps you should use. The biggest issue with DBSCAN, which you will shortly see, is that it performs poorly on clusters of differing densities. Here we see the clusters are of similar densities. With the right parameters, DBSCAN works well. Now I will change the density of the outer donut. No matter what combination of eps and min samples you use, DBSCAN will not provide good clusters. You can try this for yourself. The solution is to use optics, which is an extension of DBSCAN that works well with clusters of differing densities. There are two types of hierarchical clustering, the first being agglomerative clustering or bottom-up. Each data point is treated as its own cluster, then merged iteratively. The second is divisive clustering or top-down. All points start in a single cluster and then are iteratively split. Hierarchical clustering is more computationally intensive than centroid and density-based clustering, with divisive clustering being the most intensive. As such, agglomerative clustering is more commonly used and will be the default when discussing hierarchical clustering. Before explaining the algorithm, we must discuss linkage methods. Linkage methods are how we can define distance between clusters. The following shows the 5 most common linkage methods. Agglomerative clustering is quite straightforward. First, make each data point its own cluster. Secondly, compute the distance between all clusters based on a chosen linkage. Thirdly, we want to merge the 2 closest clusters based on the previous step. Fourthly, we repeat steps 2 and 3 until all points are merged into one cluster. The last step is to visualize the result as a dendrogram. We can visualize each step of the algorithm. For this example, we use single linkage. In the first iteration, we treat each point as its own cluster, and then find the closest cluster using single linkage. The first 3 points form a cluster and the last 3 points form another cluster. Additionally, note how the distance corresponds to the dendrogram. In the second step, there are only 2 clusters, meaning they are each other's closest cluster. The last step shows a single cluster of everything. For the same dataset, choosing different linkages can cause the dendrograms and thus the clusters to look different. Typically, ward, complete, and average are the preferred linkages because they produce balanced dendrograms. Centroid linkages is not preferred because it can cause inversions, such as in this example. Inversions are when clusters are joined at a height lower than either of its individual clusters, and they make dendrograms less interpretable. To run the algorithm, simply add the data and the linkage method as parameters. The horizontal lines represent the merging of clusters. The height of this line indicates how far apart the clusters were when they were merged. The higher up this line is, the more dissimilar the merged clusters are. We can draw a horizontal line through the dendrogram where each vertical line it intersects is treated as a cluster. The example below shows k equals 4. By doing this, we can essentially choose k from a single dendrogram. Large datasets can become slow and the dendrogram can become massive, so it should only be used for small data sets where the data points are hierarchical. A good example of this would be seeing which species are more similar to each other based on genes. Although I use the term function parameters, the values such as k and min samples are not parameters, they're actually hyperparameters. The difference is that parameters are learned from the data during training, such as the coefficients of a linear regression model. Hyperparameters, on the other hand, are set before training. This table summarizes the characteristics of the most commonly used algorithms we covered in this video. Thanks for watching and remember to subscribe.